In this lecture, I'm going to try something a little bit different. What I'm going to do is, since I have written down the lecture notes already, I'm just going to go through them. We're going to start by, in this lecture, looking at row operations and elementary matrices. However, before we do so, we want to just look at the matrix rules that we find in the other videos. So we just want to do a quick review of some of them. Matrix addition and the scalar multiplication through of matrices. So let's let A and B be two matrices that have compatible dimensions. Remember, that's very important if you're adding or subtracting, or if you're multiplying matrices. If you're adding two matrices, then the number of rows and the number of columns in each will have to be the same. And if you're multiplying, then the number of columns in the first matrix must equal the number of rows in the second matrix. So assume we have two matrices A and B. They're square, or at least they're compatible in some other way. They have the same number of rows and the same number of columns. So the first property is commutativity, which says that if you have matrix A and you add to it B, that's the same as if you start with B and then add A. Associativity. If you have three matrices now, A, B, and C, and they're all compatible in terms of number of rows and number of columns are equal, then it does not matter if you first add B to C and then add that afterwards to A, or if you start by adding A plus B and then subsequently adding C. The third property is distributivity of a scalar. So in this case, if we have a scalar alpha and we have two matrices A and B, we can either add the matrices together first, so we add A and B first and then multiply through by the scalar, or we can multiply through by the scalar. First we multiply A by the scalar, then B by the scalar, and then we add them up, and those results again will be the same. The fourth property is that if B is a matrix of zeros, then if you add B to A, that's the same as adding zeros to A, which just returns A. If we have two scalars, alpha and beta, and we add them together and then multiply the matrix A by those scalars, that's the same as if we were to multiply A first by scalar alpha and then by scalar beta and then adding the two together. The sixth property says that if you have two scalars alpha and beta, if you first multiply matrix A by beta and then by alpha, it's the same as if you multiplied alpha by beta and then multiplied through the matrix A. If you have a scalar 0 and you multiply that through A, you get a matrix 0. And if you have a scalar alpha and you multiply it through by a matrix 0, you get the matrix 0 back. Okay, so now let's look at elementary matrices. And we denote them with a large E. They have to be non-singular, and if you'll recall, non-singularity implies that the determinant of that matrix is not 0. The inverse of an elementary matrix is also elementary, and we denote that an elementary matrix with row I and row J, if those are 0, then we get an identity matrix of size P. If we take an elementary matrix of dimension P by P and any matrix A of the same dimensions, P by P, then multiplying E by A is a matrix which results when some elementary operation is applied to A. All right, so what we're going to be doing is taking this elementary matrix E and then multiplying it by A. And this elementary matrix E, we will see, has some means of interchanging rows or multiplying through by a row. So the elementary row operations that we're interested in constitute three. Okay, first we can interchange two rows. All right, we can just interchange two rows. We can replace a row, and we denote that row R with the arrow above it to indicate that it's a vector. So in other words, it's a row of a matrix. If we multiply the elements in that row by C, this constant here, then we basically, the elementary row operation replaces the original row with one that C multiplies through R. But C has to be non-zero. Okay, it cannot equal 0. Third property is the third type of elementary row operation is where we replace row 1, let's say, with itself plus a constant multiplied by row 2. So in other words, E P by P is a matrix produced by applying exactly one elementary row operation to that matrix IP. Okay, so we can think of these as a type of elementary operation. So just in reviewing, a type 1 is row interchange. So EIJ then is the elementary matrix obtained by interchanging rows I and j of the matrix IP. And we'll get back to a little bit of detail here, how that works shortly. Type 2 is where EI, so a particular row of I, is multiplied through by C, and we basically multiply that row I of the matrix large IP by C not equal to 0. And the third type is that any row ij multiplied through by C is obtained by adding CRJ. So row RJ is added to row I. All right. Now, the determinants in each of these three particular types of elementary operations are given by the determinant of the first one would be -1. So that's the case where we basically interchange rows I and j. The determinant of the second, where we multiply a particular row through by a constant C. The determinant in that case is C. And the final one is that we take one row and we add to it C times another row. So the new row is the old row plus C times a new row, and the determinant in that case would be equal to 1. So if E is an elementary matrix and A is the matrix that we're interested in looking at, then the determinant of EA is equal to the determinant of E times the determinant of A, which is a standard property of determinants to begin with. All right, so now let's consider a particular A matrix. So we have that matrix A, which looks like this here, and you can pretty well see right away that the determinant is non-singular. In other words, it's not going to be 0 because you've got elements in each of the rows or each of the columns. And the vector x is a column vector of x1, x2, x3, and the right-hand side of the expression ax equals b. The right-hand side is a column vector of -1, 1, -2. And we construct what's called an augmented matrix by simply placing matrix A and B side by side. All right, now, given that, you could see here that we have the original matrix. We can look at the elementary row operation, and then this elementary matrix, this matrix here, tells you how this particular elementary row operation works. So what we would do is we'd multiply A by M1, and that would give us the revised matrix. All right, and notice that M1 I had earlier referred to as IP. So my MP would be equal to this IP. All right, so that's the first kind of elementary row operation. So we take row 2 here and we add to it 2 times row 1. The second one here is where we interchange rows 2 and 3, and this matrix M2 shows you what you'd have to multiply it by, or how that would be done using that, what we have referred to as an I matrix, and here it's called an M matrix, the elementary matrix. The third is which is simply multiplying or replacing a row with a multiple of itself. Here we use 1/2, and that illustrates the fact that you don't need to have always whole numbers in your elementary matrix. And the final one here is simply where we replace row 1 with a multiple of some other row, which is similar to the first one that we looked at. All right, where we have row 2, all right, this one up here, row 2 replaced by row 2 plus 2 times row 1. Here we have row 1 replaced by row 1 minus 2 times row 3. And you'll see that these 4 elementary operations result in an identity matrix there. All right, and then this would then be the solution to this vector x. So that tells us x1 is equal to 1, x2 is minus 1, and x3 is minus 1. We can also find the trace of a matrix. So we let A be a square matrix given by, that's of dimension p by p. And the trace is simply the sum of the elements down the diagonal. All right, and that's shown right here. So these are the sum of elements on diagonal. And we also have this property that trace of AB is equal to the trace of BA. All right, finally, for this lecture, we want to consider what's a natural basis. A natural basis is a vector, and we often denote those vectors as E1 would be 1, 0, E2 would be 0, 1. So these are vectors that give the direction in the standard coordinate system. Okay, so vectors 1, 0 and 0, 1 form a natural basis for two-dimensional space. So we'd have, here is our vector E1, and this would be our vector E2. This would be this would be your y-axis, your x-axis, and this would be a point 1, and that would be a 1 here as well. And we have 0. In 3 space, or 3 dimensions, you have vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, and they form a natural basis for R3. So think of this graph that I've got in red here, and now add another dimension to it. How do we represent the vector 3, 4, 5 in 3-dimensional space? Well, to do so, we simply look at this. How do we represent the vector 3, 4, 5 in 3-dimensional space? So in standard Cartesian coordinate system. All right, so these are now, I've put these as column vectors, and what we want to show is that we want to solve for C1, C2, and C3. All right, and this is the natural basis. All right, these three vectors form that natural basis, as I pointed out right here. All right, and what we do is we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and that ends up being simply a vector of C1, C2, C3. All right, and when you solve that, you get that solution, so you get that back. So the answer here is you multiply these E1, if you like. So what we have is basically C1, E1 plus C2, E2 plus C3, E3. Okay, that's your standard natural basis. Now, suppose we wanted to look at this a little differently, and we're looking at a different basis now. So consider the scalars required to determine whether vector 3, 4, 1, what it looks like relative to the bases 1, 0, 0, 1, 1, 0, and 1, 0, 1. All right, so let's set it up as before. So we have 3, 4, 5 is equal to C1, and this is then the bases there, that one there, and this one there. And when we do that, we get C11 plus C2 plus C3 as our first element. When we do that, we get, we have the following. Then C2 is the second element, C3 is the third element. It's very quickly you can see that C2 has to be 4, C3 has to be 5, and then C1 is simply C1 plus C2 plus C3 is equal to minus 6. We solve for C1, and we find that indeed it's minus 6. All right. So that's how we deal with a change in basis. So the ordered triplet, minus 6, 4, 5, constitutes the coordinates of the vector 3, 4, 5 relative to this basis given by these three basis vectors. So why do we need to know about natural bases? Because they are used in finding eigenvalues and eigenvectors. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.